So basically, if I run printcomp with this particular code, there, let's run it. Okay, it will just give me those particular components that I've asked for, right? It just gives me the correlation matrix, the eigenvalues, and the score matrix plot. Now, if I run it again, but without that command there, this is on the x123, x1, x2, x3 data set, I get more information, right? Because I haven't specified, I just want these things. Right? So now if I'm looking at the bottom, I get all that. Plus, I get something called a scree plot and eigenvectors. But I still get my correlation matrix. I still get my eigenvalues, right? But now I also get some information about the data set, the simple statistics, etc. Right, so let's talk this through. Right, so I've got three variables, x1, x2, x3, right? I can look at the correlation matrix, and look, I can see that there are some heavy correlations going on here, 0.6995 and 0.706. And that is because, in fact, x3 is being created to be a perfect linear combination of x1 and x2. Even though it's a linear combination of them, when you look at the individual correlations, you don't see it, right? You see it's heavily correlated, but you don't see a perfect correlation because it's perfectly correlated with some value times x1 plus some value times x2, right? It's perfectly correlated with the combination of those first two things. So in fact, x3 is completely redundant in our data set. We actually have all the data could be mapped onto a plane with this data set, but it's not evident just looking at the correlation matrix, is it? Right? All you know is that there is correlation going on here, high correlation. So what happens? Well, okay. I've got my eigenvalues, right? What are my eigenvalues? My eigenvalues, as we will learn, are the amount of variation that I've got when I project the data points onto those axes. So we basically have two positive eigenvalues and one that's zero. I've got a zero eigenvalue, meaning that we have actually, the third axis isn't containing any information once it included the first two. So that first axis contains 66% of the variation in the data, right? The second axis contains 33%, plus or minus a little bit, right? So combined, the first two axes contain all of the information. The addition of a third axis doesn't help at all, right? Because basically, all the data was sitting on a plane, right? So that's what's going on here. I'll teach you about scree plots soon. And this is what happens, right? And look, here's the first axis, second axis, the third axis. Well, the data line of point. It's useless, okay, given the first two. All right. So we can start to see. We haven't actually got the useful plots yet, but this is sort of the deconstruction of what's going on for that lab. Okay, does that make sense? Are there any questions? Do you still have any questions? Josh, does that answer your question?
Yeah.
Okay, Liam.
Does the output from the proof then help you identify specifically which variable is linearly dependent on it?
All right, so that's a very good question. Does the output from printcomp show you which variables are really important, right? The answer is yes in the eigenvectors. Right, so we know that the first eigenvector is, in some ways, the most important eigenvector, right? We know that that eigenvector is a linear combination of the first three variables, x1, x2, and x3, right?
Yeah, sorry, I mean, when you know that there is you contrive the perfect linear combination.
Yeah, this is contrived, you're right.
Yeah, so can we look at the output and identify which of those input variables, the original variables, is completely redundant from the others? So I'm not so concerned about which.
Yeah.
By the first principle redundant and how it fits on those variation.
Yeah. You want to know, well, okay, we know x3 is the contrived one, and it's simply a linear combination of the first two, right? Yeah, that's a good question. Can you determine which because it doesn't work, you could view it in more than one way. You could say, given x3 is redundant given x1 and x2, or x3 is, it works the other way around as well, right? And these two variables, it is actually completely contrived. But since it works both ways, it's kind of difficult to state, well, this variable is redundant. It's just, that makes, it is correlated with these variables, these sets of variables. But that just means that it's correlated with, right, in real life. So people don't usually say, hey, look, this particular variable is redundant. This is an unusually contrived example.
Right.
So I can't see that, yeah.
You'd have to, if you wanted to drop a variable that linearly dependent on others,
Yeah.
you just have to choose from make an arbitrary decision about which one to drop in.
Yeah, at this point in time, yeah. So, but of course, the whole point of doing a PCA is you're not dropping a variable, you're dropping PC axes instead, right? So we're creating a new basis here.
More in like in the context of if you're wanting to identify the specific purpose for using it, if you're wanting to identify linear combinations.
Right, yeah. But if you're trying to find which variables to drop, this is not the technique to be using, right? You should be using a VIF or some shrinkage method like that instead of a PCA, which is just going to create axes that are actually just weighted linear combinations of everything. So it's difficult to see which variable is actually redundant. It's not the purpose of it. Right? It's a very good question.
Dr. Amosreti, according to the results I'm having, I do not have a significant correlation between x4 and x1.
X4 and X1. Right, so this is for
I'm sorry,
X3 and X1. A significant correlation, what do you mean? X3 and X1 are highly correlated. They have 0.6995.
It's 0.69, but in my case it's 0.4.
Really? Shouldn't it be identical?
0.4.
So what variables have you got in your...
This is maybe the data set.
Have you got X1 and X2 and X4? Right, so I've got X1 and X2 and X3.
No, that's the 3.
No, we have 3, 4.
Right.
Yes. Okay, so the point was X4 is not a linear combination of X1 and X2. It is, they are all uncorrelated with one another. That was the whole point. Right? That was the first part of the lab. Yeah. So remember, we ran this twice, right? If you look at the code, right? First we did it between X1, X2, and X4. And these are all basically independent of one another, right? And that was fine. And what happened when we ran this is, if you look at it, because they're all independent of one another, we don't actually gain anything using the PC in the PCA. Have a look at how much variation is explained by these guys. Well, the first axis explains 34%, roughly a third. The second axis explains roughly a third. The third axis explains roughly a third, right? So we're losing a third. If we just choose the first two, we're losing the third variable anyway. So it doesn't really help in that case, because we have three variables that are essentially independent of one another. Right? So this is the situation. Think of your data as sitting in a ball, right? And we're just choosing two axes somewhat arbitrarily through that ball. Right? There's no structure to it. There's no real strong correlations. If there's no correlations, then your data is sitting in this three-dimensional ball. Right? And how we choose our axes is somewhat arbitrary. That first axis is just maximizing, probably due to sampling variation. So you're going to get something a little bit more than chance, a little bit more than 33%, but it's not a lot more than 33%. So this first example is sort of this pathological case where there is no structure to the data. There's no real correlations between the variables, right? These are all 0.04, 0.005, and 0.01, right? There's no real correlation in the data set there. In that case, the PC is not really helping much. The PCA is not helping much. Yes? Right, that's called the Kaiser-Gutmann criteria. So the question is, well, how many PCA axes should I choose, right, essentially? There are a few different ways of doing this, and I will cover this in like this. Right. As I said, this is a ongoing field of research, right? It's a very big deal. So if you think about it, right, with a correlation matrix, the sum of all your eigenvalues is equal to the sum of your variables, Right? Since we have three variables, the sum of all your eigenvalues, since we are deconstructing the correlation matrix and not the covariance matrix, which is what we usually do, the sum of all this just equals 3. Right? If we had 4, the sum of it, if we had 4 variables, these would all sum to 4, all of the eigenvalues. Right? And so the amount of variation that is explained basically is going to be, in this case, 1.04 divided by 3, right, which gives me 34%. So on average, right, they would give an eigenvalue of 1, right, because if the sum of the eigenvalues is 3, you know, the average eigenvalue is 1. So the Kaiser-Gutmann criteria is saying, hey, look, eigenvalues bigger than 1 are useful. They're explaining more variation than you would expect. Eigenvalues less than 1 are explaining less variation than you would sort of expect by chance in some way. Right? So that is one of the criteria that it would use. It would say, hey, look, but here's the problem. This value is less than 1, but it's only just less than 1, actually. It would say, just grab the first 2, but really all 3 axes are pretty much equally important. Right? And you can see this by the amount of variation they explain. The first one explains 34%. The third one explains 33%. The second one explains 33%. And the last one explains just a little bit less, 31%. Right? So cumulatively, the first 2 axes explain 68%. And the third one, there's still a sizable amount of variation that's left, that's unexplained. So, but we will talk about this, and we'll talk about scree plots and ways of working out, well, how many dimensions should I choose, right? The short answer is people tend to choose 2 if they want to plot. That's all there's no choice in the matter, right? 2 or at most 3. And then you just say, well, how good an explanation is this of the real, of the full dimensional data set? And you just say, well, this 2-dimensional plot explains 68% of the amount of variation that you see. Okay, so is that all right? Any other questions about the lab? These are some really good. I'm enjoying having these discussions. Anything else you guys want to know? Well, let's not jump ahead because I will talk about it a bit more. So this is getting to what Chow was saying actually about the geometric properties of PCA. What is PCA doing? Well, it's trying to minimize the information that is lost, right? So if you draw an axis, a single axis through a 2-dimensional data set, right, what you're trying to do is minimize these distances, right? Think about it. If all the data lay perfectly on a straight line, right, then your axis would explain that data perfectly. And the variations around that line would be 0. You've lost 0 information. So this information, if I project the information, the data, onto that line, that's the amount of information, that's information that I'm losing, right? The distance is in this way. If I, for example, had another data point, here's a data point here, and I had another data point that was way up here, they would look to be exactly the same thing. So I'm losing information, right, in that. So PCA is trying to minimize the sum of the squared distances to the axis of the PC. To this axis here. That's what it's trying to minimize, this thing here. Least squares regression is trying to minimize the sum of the squared vertical distances relative to whatever our response is. So it's slightly different. Okay, so often, when I say often, regularly people use PCA axis scores as their input variables into a regression. Right? And this is pretty useful because each axis is orthogonal to the others. So rather than using x1 and x2, they've used PC1 and PC2. And we know that PC1 and PC2 are going to be completely independent of one another. So I will have no problems with multicollinearity. Well, I was incorrect when I say completely independent. What I mean is that they are uncorrelated with one another. They are not necessarily independent of one another. Okay, so go ahead and do lab 3 at this point in time. And I will talk about scree plots, etc. And then in the afternoon, we will do the movie. We will do the movie data set, that we created. Has everybody entered the data into the Google spreadsheet? Okay, that's great. I'm looking forward to seeing what we can do. Hang on, I'll just see.